Ladies and gentlemen, welcome to Cook Like You Mean It with your host, Master Chef Jason Trachtenburg.
Hello, and welcome to another episode of Cook Like You Mean It. I'm Jason Trachtenburg, and this is my special guest assistant chef, Soce the Elemental Wizard. Soce, it's great to have you on this week's show.
It's great to be here, Jason.
Okay, let's get things started. Today we're going to cook beans. My favorite are black beans. What are yours, Soce?
I'm really into split peas these days, but I also enjoy lentils.
Those are some fine legumes. Okay, the first thing you need to do is pour 10 fluid ounces of water into a pot. Well, isn't that something? All I have here is a 4-ounce cup and a 7-ounce cup.
There must be some way you could combine those two cups to make 10 fluid ounces.
Why, yes, there is. You just fill up the 7-ounce cup to the brim. Then you pour it into the 4-ounce cup until it's full. That leaves 3 ounces remaining, which you pour into the pot. Finally, you fill up the 7-ounce cup once again and dump that into the pot, which makes a total of 10 ounces poured into the pot.
Very impressive. Hey, is there any way you could use those 2 cups to make just 1 fluid ounce?
Certainly, sir. Just fill up the 4-ounce cup once, then pour it into the 7-ounce cup. Then fill up the 4-ounce cup a second time. Next, pour it into the 7-ounce cup until the 7-ounce cup is full. You will have 1 ounce remaining in the 4-ounce cup.
Brilliant. You got me thinking now. Is there any combination of 2 cups where no matter how many times you pour them back and forth, you won't be able to create a specific amount of water? Just to be clear, each cup must contain a positive integer amount of fluid ounces, and we're trying to use them to create other positive integer amounts.
Yes. In fact, there are many combinations that will cause problems. If both of the cups share a common prime factor, then you will not be able to combine them to make any number of fluid ounces other than multiples of that prime number.
And a prime number is?
Any positive integer greater than 1 that can only be evenly divided by 1 and itself. The first few being 2, 3, 5, 7, and so forth.
Oh, so for example, since 2 is a prime number, then if both cups were to hold even number amounts of fluid, you'd never be able to combine them to make an odd number amount of fluid.
Exactly. Or, for instance, if one cup holds 10 fluid ounces and the other holds 25 fluid ounces, you'll be able to pour them back and forth to make 5 fluid ounces, but never any positive integer less than that. Plus, you also won't be able to make 6, 7, 8, or 9 fluid ounces of any number of fluid ounces that isn't divisible by 5.
Do you know how to determine the prime factors of a number?
Sure. If the number's small enough, you take the square root and then see if any prime numbers divide into it evenly, where those prime numbers are less than the square root of that number. Let's take 189. Since 189 is between 169,
13 squared,
and 196,
14 squared,
then that means its square root is between 13 and 14. So you just need to see if it's divisible by 2, 3, 5, 7, 11, or 13. Well, it turns out that it is divisible by both 3 and 7. In fact, when broken down to just the primes, you'll see that 189 equals 3 to the 3rd times 7.
Very thorough explanation. What if the number is huge, such as greater than 1 trillion?
Didn't you use the number 1 trillion in a recent episode?
Why, yes I did.
Anyway, it's very difficult to break extremely large numbers into their list of prime factors. In fact, top agencies specializing in covert operations like to use that principle to create their secret codes. Hey! It looks like our beans are all ready.
Delicious.
Math problems, it's the end of the show. We are letting you go till the next episode. Try to crack the code, keep solving the play. Loosen up, do a couple math problems a day.